Today we will continue the discussion on Boolean algebra, but before that first we see the answers of the last two lectures quiz, the lecture 5 and 6 quiz. So, the first question was the two inputs A and B are inverted and applied to an OR gate, construct the truth table. Now, A and B are inverted. So, if A takes the values 0, 0, 1, 1, this is complement of A or negation of A will be 1, 1, 0, 0, it is inverted. Similarly, if B has the value 0, 1, 0, 1, then negation of B will be 1, 0, 1, 0. Now, what will be the negation A, non-negation B, because these are the two inputs. See that if negation A means 1 and negation B is 1, if we take OR 1 plus 1, then it will be 1, then complement of that will be 0. So, 1 plus 1, 1, complement of that becomes 0. Similarly, 1 plus 0, it is 1, complement of that 0, 0 plus 1, 1, complement of that means NOR is 0, 0 plus 0, that is the OR of A and B, negation A and negation B is 0, complement of that becomes 1. Now, if we ignore negation A, negation B and see only A, B and our output, then we see that actually this is nothing but the AND, because 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So, this is nothing but the A and B. So, negation A, non-negation B is equivalent to a two input AND gate. See our second question. Second question, that an input A is inverted and applied to an AND gate. The other input is B. The output of the AND gate is applied to an OR gate. A is the second input to the OR gate. Draw the logic circuit and the truth table. So, first we see the logic circuit. Say input A is inverted. Take the input A, it is inverted. So, this is my input A, it is inverted and applied to an AND gate. So, this is my one of the AND gate. The other input is B. So, this is my other input. The output of the AND gate is applied to an OR gate. So, this is my OR gate. A is the second input to the OR gate. So, A is the second input to the OR gate. Draw the logic. So, this is Z, the output is this. Now, see, then what is this Z? Z is nothing but, first this is A bar B. So, this OR gate one input is A. So, A plus this is A bar B. So, this is my logic circuit. Then what will be my truth table? We see now the truth table. See, what we have seen, that output Z is nothing but A plus A bar B. So, if we draw the truth table, these are my two inputs A B and this is my output Z. I take all possible values of a b 0 0 0 1 1 0 1 1. Then what will be the value? Say this is a bar means 0 bar. So, a bar a plus a bar b, I take one example that 0 plus 0 bar dot 0 means this is 1 dot 0 0 0 plus 0 0. Similarly, it will be 1, this is 1, and again if it is, that means for 1 it will be 1 plus 1 bar 1. So, this becomes 0, but this becomes 1 plus 0. See, this is 1. Now, see what is actually this truth table is 0 plus 0 0, 0 plus 1 1, 1 plus 0 1 1 plus. So, if we consider the OR gate, that means this is nothing but a OR, that means A or B, or the simple 2 input OR gate whose inputs are A B. So, the previous page, that the circuit we have got, the logic circuit, that is nothing but that is equivalent to a 2 input OR gate. Now, our third question was the draw the logic circuit for the Boolean expression z equal to a b bar plus a bar b plus a plus b bar dot a. Now, if we draw the circuit, then what will be the thing? See, first again there are 2 inputs A and B. So, this is my A, 1 2 input AND gate. Okay. Now, this is B bar, means B is complemented. So, one inverter I put NOT gate, this is my B. So, this is the A B bar. Now, A bar B, I take another AND gate, then this is inverted, B is the another input. So, this is my, this AND gate is the for the second expression A bar B. Now, another is A plus B bar dot A. So, I need another AND gate whose one of the input is A. Another is the, see, A plus B bar means this is the output of a 2 input OR. So, if I put a 2 input OR, then this is the output. What is the input of 2 input OR? One is the A itself, another is the B complement. So, I can take B complement from directly from here, or I can take B and I complement that and this. So, these are the 3 inputs. Now, if one 3 input OR gate I draw, and so this is my logic circuit for this Boolean expression. Okay. So, now we start our today's lecture. We continue the Boolean algebra. Now, last day we mentioned or we did the postulates of Boolean algebra. Again, if I summarize the last day's thing, that from the duality principle of Boolean algebra, the following 4 postulates we have defined. What is that? So, if A is a Boolean variable, then a plus 0 is a plus negation n means complemented a is 1, a plus b is b plus a commutative, a dot b plus c is a dot b plus a dot c. Now, the counterpart for these 4 postulates are, if this plus means already we have defined this is nothing but a OR. So, this OR can be replaced by AND, then this is a dot 1 equal to a. This is a dot negation a equal to 0, a dot b equal to b dot a, and a plus b dot c is a plus b dot a plus c. So, now today we define some of the theorems, the Boolean theorems of Boolean algebra, and mainly they are based on these open axioms or the postulates what we have defined. Now, the first theorem we see that this is a plus a is a. Similarly, the counterpart is the a dot a is a. So, how we can tell? Now just to prove this thing or see the validity of this theorem, we will use the postulates what already we have defined. See, a plus a is a plus a dot 1 from the first postulate. Now, 1 we can easily replace by a plus negation a. Now, if we apply the postulate 2, that means our distributive postulate, then this is a plus a dot negation a. Now, from postulate 1, that means the counterpart of postulate 1, that we know that a negation a is nothing but 0. So, this part, the second part becomes 0. So, this becomes a. So, a plus a equal to a. Now, if the plus is replaced by dot, a dot a. So, a dot a is a plus 0, this is 0, we have defined that additive identity. So, from postulate 1 we have added 0. So, this is now 0 we can define a negation a, just now we have used from postulate 2. Then if I take the common, then a is a plus negation a. Now, see, a plus negation is nothing but 1. So, this is a dot 1 and this is a, because from the postulate 1, a dot 1 is a. So, a dot a is nothing but a. So, this is the first theorem of Boolean algebra. We see the second theorem. Second theorem tells that a plus 1 equal to a and a dot 0 equal to 0. Now, a plus a equal to 1 dot a plus 1 equal to a plus negation a, because 1 is nothing but a plus negation a, and as it is we keep a plus 1. Now, if we take or just distribute that thing, then a, this is a, then negation a dot 1. Now, negation a dot 1 is nothing but negation a. So, a plus negation a is 1. Similarly, that this is a dot 0 equal to 0 by duality, because duality means that dot is plus is replaced by dot and thus by using the similar way we can prove that this thing. Now, theorem 3 is the involution. What is the involution property? That negation of negation A means if I take one Boolean variable and twice we take the complement twice, then we will get the variable itself. Say A is a Boolean variable. First we take one complement of A, the negation of A. Again I take the complement of this thing, means the complement of A, we will get the variable itself, means A. Now, from postulate 2 we have already read that A plus negation A is 1. See, if my A is 0, so 0 plus 1 is 1. If my A is 1, because it is a Boolean variable, it can take only two values, either 0 or 1. So, if it is 1, then it will be 1 plus 0, 1. Now, A plus negation A is 1 and A dot negation A is 0. This is from my postulate 2. Now, or if I write negation A plus A, just change this thing, this is equal to 1 and negation A dot A equal to 0. I mark this as a equation 1. Now, these two define the complement of A. Now, if we replace A by negation A, so in this expression if I replace, because see that A is a Boolean variable. So, A can take two values, either 0 or 1. Now, if I take the complement, then I will be taking negation A, and what will be the values? If A is 0, then negation A is 1. If A is 1, then negation is 0. See, that means if A is a Boolean variable, negation is A is also a Boolean variable. So, I can easily replace A by negation A. Then what will be the postulate 2? That negation A plus negation A. Now, A is replaced by negation A. Negation of negation A equal to 1, and here A means negation A dot, this negation is negation, A is replaced by negation A. So, negation of negation A equal to 0. I mark this as equation 2. So, from equation 1 and equation 2, what we get? That say this is equation 1 was negation A plus A equal to 1. Here equation 2, this is negation A plus negation of negation A equal to 1. So, this means A and negation of negation A is same. Similarly, from the counterpart, or that if the operator is dot, then this part is negation A, same. Here the right hand side is A, or the next term is A, and here this is negation of negation A, then this is equal to 0. So, from equation 1 and 2, what we see that A, if we replace A by this, then actually this is same. So, that means from equation 1 and 2, negation of negation A is A itself. This property is called the involution. Now, theorem 4, these are associative. Already we have seen that property, the commutative, when we have taken the two Boolean variables, that A plus B is B plus A. Now, if it is 3 variable we take, that means A plus B plus C is, if we take the operator operating on the first two variable a plus b, and then on c plus c it will be same. Similarly, if plus is replaced by dot, then a dot b dot c equal to a dot b dot c. So, the associative property tells that if we take 3 Boolean variables and the order of the operator, that means if in the left hand side the operator is operating on the b and c, the last two operands or the variables, and then it is operated on the first variable, the result will be same if we take the order of the operators in different way. That means, the operator is first operator on the first two variable and then on the last, it will be same, and this is same as if the plus is replaced by dot. Theorem 5 already we discussed in the last class, but again if we summarize, this is nothing but De Morgan's law. So, De Morgan's law, that if plus is replaced by dot, then the Boolean variable will be replaced by the complement of that or negation of that. So, that means that if say we are taking negation of a plus b, the two variables, then this is same as that of negation a dot negation b. See that here operator was plus. So, first this plus is replaced by this dot, and the a and b operators, a is replaced by negation a and b is replaced by negation b. Similarly, if I take the left hand side the dot operator, that means this dot, this is replaced by plus, and if a is replaced by negation a and b is replaced by negation b, then they will give the same output. So, this is nothing but our De Morgan's law when we are taking only or it is operating on two variables. Now, theorem 6 is the absorption, that see a plus ab equal to a, and a dot a plus b equal to a. See how we can tell this expression is true. See, first if we see the first part a plus ab. What is a plus ab? See, a plus ab, if I take a means a dot 1 from the postulate 1 and ab as it is I can. Then if I take a common, then this will be a dot 1 plus b. Now, b plus 1 is nothing but 1. How? Again by truth table I can see that thing. Say b plus 1, I am telling this will be 1. Why? So, b can take two values, either 0 or 1. So, if it is 0 plus 1, see this will be 1, or if it is 1 plus 1, this will be 1. So, we can easily check that actually 1 plus b is b itself, 1 itself, 1 plus b is 1. So, we replace. Now, again if it is a dot 1, now this will be a. Similarly, I can tell that a dot 1, again he can take two values 0 or 1. So, if it is 0 dot 1 means this is 0 means A. What was A? And 1 dot 1 means 1, that means the A value. What was A? So, actually A dot 1 is A itself. Now, if we replace for the B part to be proved, if we replace the plus by dot and the dot by plus, that means by duality principle means if we exchange the dot by plus and the plus by dot, then we will be getting the same result. So, these are my 6 theorems of Boolean algebra. Now, just as I mentioned that these Boolean algebra theorems can also be checked by truth table. Just now we have seen for one simple example that 1 plus b equal to 1 or a dot 1 equal to a. Similarly, if I take say for the theorem 6, what we have told that a plus a b equal to a. See, if I draw the truth table, then a can take 4 values, actually 2, there will be 4 combinations because there are 2 variables. So, this will be 2 variables, that means and any one can take 0 or 1. So, it will be 2 to the power 2 means there will be 4 combinations. So, 0 0 0 1 1 0 1 1. What will be AB? Then 0 0 0 0 1 0 1 0 0 1 dot 1 1. What will be A plus AB? See that 0 plus 0, this is A, this is AB, this is 0, 0 plus 0, this is 0, 1 plus 0, this is 1, 1 plus 1, this will be 1. Okay. So, by truth table also, by drawing the truth table also, we can see that A plus AB, A plus AB is 0 0 1 1. See, these are 0 0 1 1 and see our A is also 0 0 1 1. So, actually A is equal to A plus AB. So, what we have proved by the help of the postulates, that also we can check by drawing the truth table also. Okay. Now, the operator precedence of Boolean algebra. So, just now what we have see that actually our plus is nothing but our OR, dot is actually when we are taking, this is my and negation is our or the complement, this is the not in digital designs. Now, in Boolean algebra, these operator precedences for evaluating the Boolean expression, first is the parenthesis, that means expression inside the parenthesis must be evaluated first. Not is the next operation and that is the complement. The next we will do the and, this is the next to not, and or is the next to and. So, these are the precedences in this order the operator precedences when we will evaluate one Boolean expression. Now, a algebraic manipulation of Boolean functions. So, a Boolean function is an expression formed with binary variables. A binary variable can take the value 0 or 1. Boolean function can be minimized by algebraic manipulation and no specific rules to follow. Though we have read the postulates and the theorems, so when we will want to minimize or when we will be minimizing the Boolean expression, we will do the algebraic manipulation, and this algebraic manipulation consists of the postulates and the theorems, but this is on that cut and try method, cut and trial. There is no specific rules that which one will be followed when. So, this we will see next. See, I want to minimize, or I am telling that simplification of some Boolean function. Say I have one Boolean function a b plus a bar c, mainly the negation a c. So, our negation a and this is same as a bar, these are all complement of a, complement of a. So, if I have one function say f equal to a b, a bar c, b c, how we can simplify this thing? Now, I know the 4 postulates and 6 theorems. Now, I have to apply just to simplify or to minimize this expression. See, a b as it is I have kept a bar c, and now this b c I have kept b c as if this is 1, this is b c, see I am writing b c dot 1. So, 1 is replaced by a plus negation a from our postulate. A plus negation a is nothing but 1. Now, so this is a b. Now, this if I distribute this thing, that means this is the distributive law, this is b c dot a plus b c negation a. So, b c a means a b c, that I have taken here, and this is negation a b c next term, and negation a c means a bar c, that will come here. Now, from here if I take common a b, this will be a b into 1 plus c, plus here if I take common negation a c from these two term, and then 1 plus b. Now, we know 1 plus c is nothing but 1 plus c is 1, already we have seen from the our postulate, and similarly 1 plus b is nothing but 1. So, this is a b plus a bar c. So, see there are 3 terms here a b, a bar c, b c, and that is actually now becomes a b plus a bar c. There is no b c term, as if b c is redundant in the expression. So, this becomes a b plus a bar c, and this is the minimum number of literals. A literal we can define as if a primed or unprimed Boolean variable, means either it is a complemented variable a, or it is normal uncomplemented, or if it is a complemented variable. So, literal we are telling this is a literal. So, this is a minimum number of literals. Now, we see the canonical and standard forms. Before we define the canonical and standard forms, first we define the min terms and max terms. So, binary variable may appear either in its normal form, just now I mentioned A, or its complement form negation A. For two variables A and B, there are four possible combinations: AB, negation AB, A negation B, negation A, negation B. See, if I take two variables, if I take two Boolean variables, then either the A can be negation A also, B can also be negation B or complement also. Now, so as if I have four such variables, so what will be the combination? If I take the operator as the dot, then it will be, see, A dot B, A dot negation B, now if I take negation A, it will be negation AB or it will be negation A dot negation B. See, AB, this is same as B dot A, and all other combinations are same. So, these are the four combinations I can get. So, this is written in the second point, that for two variables A and B, there are four possible combinations: AB, then A bar B, AB bar, A bar B bar. Now, these are called min terms or standard product. So, what is mainly the product terms, or if the operator is a dot operator, then the variables operated by that operator is called the min terms. Now, for n variables, there are 2 to the power n min terms. See, just now what we have seen, say for A, there are two variables A and B, there are AB, then AB bar, A bar B, this is same as that of negation, and A bar B bar. Similarly, if it is 3 variable, this is variable 2. If it is 3 variable, then A, B, C. What will be the product terms? See, this will be ABC, then ABC means A dot B dot C. Okay. So, I am telling simply ABC. This is A, B bar, C bar. This will be A bar, B, C, A bar, B, C bar. Then it will be A bar, A bar, B bar, C. It will be A bar, B bar, C bar, then it will be A, B, C bar, it will be A, B bar, C, another is left A, B bar, C bar, A, B, C bar, A, B bar, C, then A bar, B, C bar and A bar, B, C, A bar, B, C. See, there are 8 terms, these are the terms. So, this is nothing but that if it is 2 variables, then it was, if it was for 2 variables, it was 2 square. If it is 3 variables, the product terms were 2 to the power cube, that means there are 4 terms, here it is 8 terms. So, if it is n variables, this will be 2 to the power n such product terms will be there, or the mean terms are 2 to the power n mean terms will be there. So, for n variables there are 2 to the power n mean terms. Now, each mean term is obtained from an n term of n variables, as just now I have shown. Now, we take that terms, or normally what is the conventionally how we designate these mean terms. See, these are the 3 variables ABC. Just now I have shown these are the terms. So, if it is 3 variables and we know that they can take either 0 or 1 values, then these ABC values are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, like 1, 1, 1, all 2 to the power 3, all 8 possible combinations are there, all 0, 0, 0 to 1, 1, 1. Now, that there is some convention that normally that 0 means it is a complemented variable. So, A equal to 0 here means this is denoted by the term is, this is negation A or complemented A. Similarly, that B, this is B equal to 0 means this is negation B, and C equal to 0 means this is negation C. Now, it is 0, 0, 1, so this is negation A, negation B, C, only C, this is uncomplemented. 0, 1, 0, that means negation A, negation C, but B only. Similarly, 1, 1, 1 means that is simply ABC, and these are the designation, or normally it is written like that. This is the mean terms, that small m, and this is the 0th term, means that say M0, this is M1, M2, M3. So, now you observe these subscript 0, 1, 2, 3, 4 up to 7, this is nothing but the decimal equivalent of the value ABC is taking. See, if I take this one 0, 1, 0. So, 0, 1, 0 means the decimal is 2. See, actually this I am giving that M2, this is my M2. So, the subscript is the decimal equivalent of the value ABC is taking, and in this way we represent the mean terms. So, my M7 is nothing but my ABC, and normally this is the convention that, but one can take the totally reverse one, means the 0 means the uncomplemented 1 means the complemented, but normally this is the convention, and that in this class we will follow this convention. Now, we define similarly the max terms. So, n variables forming an odd term with each variable being primed or unprimed called max term or standard sums. In the mean term, what we have seen that the operator was AND dot, and the terms are mean terms are defined that the each variable being primed or unprimed means complemented or uncomplemented, they are operated by the dot operator. Here the dot is replaced by plus, means AND is replaced by OR, and similarly the terms are defined as the sum or the max term. Here also that for n variable there are 2 to the power n max terms. See, again the same similar type of example we can see for the 3 variables. Here this is again it takes the 8 combinations for 3 variables, 2 to the power 3, 8, and see that all dots are replaced by plus. So, this is a plus b plus c, this is a plus b negation c. Now, observe one thing, that here in the mean terms, that 0 we have defined as complemented A and 1 is the uncomplemented one. Here we are taking the reverse one. Again this is a convention that in the what we have taken in the mean term, the reverse we are taking in the max term. That means that 0 is the uncomplemented one, A plus B plus C. Here A plus B plus C bar, this is my negation C, C bar. Similarly, say if I take 1 0 0 means this is A bar plus B plus C, A bar plus B plus C. See why that if I take, and okay, before that I complete this. Again designation is that similarly the subscripts are the decimal equivalent of the Boolean value that ABC is taking, and this is normally denoted by the capital M, that M0, M1, M2, M3, M7. Now, see why the reverse convention is maintained. See, if I take two values A and B, so I am taking 0, A is taking 0, B is 1. Now, for the mean term, what will be my mean term? Mean term, it will be that 0 means it will be A bar and this is B. Now, again if my AB is 0, 1 and if I consider the max term, then it will be according to this convention, it will be A plus B bar. Now, see that from using De Morgan's law, actually A bar B is that if I replace dot by plus, then the variables will be replaced by the complemented one. So, this will be A bar and this will be B bar. Now, again from the involution theorem, that complement of complement A is nothing but A itself. So, this is A and this will be B bar. So, which is nothing but our max term A plus B bar and mean term is A bar B. So, that is why the reverse convention is taken. That means, in the mean term 0 is treated as the, if A equal to 0, then 0 is treated as the complemented 1, in the max term the 0 will be treated as the uncomplemented one. Now we have already defined the max terms and min terms. So now we can define that what do we mean by canonical and standard forms. See, the Boolean functions expressed as sum of min terms or product of max terms are said to be canonical form. What do we mean? That see, if I have one expression and the terms are either related by the sum of min terms, means their min terms means their product terms, and they are related by plus sum, and max terms means they are plus terms and they are the product of, they are related by the product, then it will be in the canonical form. So, if I take one simple example, what will be the thing? See, some of the min terms are, if I take 3 variables, okay, A, B, C. Some terms are say A, B, C bar, say A, B itself or A, B bar, and take say B, C. So, these are the 3 min terms. Now, if some expression, say I am taking E1 equal to A, B, C bar plus, see these are the sum of product form or sum of min terms, this is one canonical form. Now, say again A, B, C are terms. Now, if I can some other expression E2 where this plus actually is replaced by dot, this plus is replaced by dot. Say here I am taking say A bar plus B, A plus C and say B plus C bar. So, I am taking this type of thing. Then again this is a canonical form. So, either this is a sum of min terms or product of, this is a product of max terms. So, any Boolean function can be expressed as a sum or ORing of min terms. Now, these are the two very important properties. Given any function, that always can be expressed as the sum of min terms. Similarly, any Boolean function can be expressed as product of max terms, that means either ORing or ANDing, and obviously it will come from the De Morgan's law, because or the duality principle, whatever we call. So, these are the two very important properties that normally we utilize. Now, today we will here we end this lecture. Again we will continue that next day, but some of the quiz question based on this lecture we see. This is lecture 7 quiz that simplify the following Boolean functions to a minimum number of literals. That means, this is nothing but the minimization of the Boolean expressions using the postulates and the theorems. This is BC plus A bar, AC bar plus AB plus BCD. And another expression is A plus C plus D, A plus C plus D bar, A plus C bar plus D, A plus B bar. So, just note that this is the sum of min terms, and the next one I have given is the product of max terms, and we have to simplify this thing. The second question is find the complement of the following Boolean functions. We have to take the complement, and again when we will be taking the complement, we will use the De Morgan's law, because complement and uncomplemented means normally the De Morgan theorem that comes into picture. So, you can use this thing. Term is B C bar plus A bar D plus A B bar plus C D bar. See, normally this is same, that complement I have mentioned already, that negation A and these are same, A bar, A bar. So, actually this expression, or say if I say this expression means this is A B bar plus C bar D bar. So, these two are same notation, complementary. Normally this denotes the complement of A or negation of A. So, this is A B bar plus C bar D bar. Again we have to take the complement of this expression. Another is, the third one is the express the following function in a sum of min term and product of max term. As just now I mentioned that the two important properties, that any Boolean function can be expressed as a sum of min terms or product of max terms, always it is true. So, based on these two properties that I have given this question, that express the following function as a sum of min term, because this is given a product of max term. Again it is not as it is product of max term, because see AB is a min term, AC is a min term. So, again this is a mixed, this is a normal form, a standard form. This is a standard form, we have to write it's this type of equation, that means it will be a only sum of min terms. In that way we have to do that thing. Today we will read how to minimize the Boolean function, but before that first we discuss the answers of the previous lectures quiz. The first question was to simplify the following Boolean functions to a minimum number of letters. First one was BC plus AC bar plus AB plus B.